Right, okay, in this video, what I'm gonna try and explain, and I'll do use the words carefully, try and explain is how a full adder works. Now in the previous video I showed you how to add two bits together and produce what the output is and what the carry value is. Okay, but in reality when we're working with numbers we generally need numbers that contain more than one bit. So what we've got to do is build a system that allows us to add two numbers together but take in account any carry value as well. So effectively what we're going to do, let's assume we've got numbers A and B and we've got a carry of C. Okay, so we're going to add the two values, the two bit values together, A and B, whatever they are, and then we're going to add to the result of that C, the value that is in the carry, whether that's a 0 or a 1. Okay, but when we do that, we're going to generate a sum from these, but we're also going to generate a carry value to carry on to the next pair of bits that I need to add up. Okay, and this system that does this is called a full adder. So in order to implement this, we've got to add two bits together. Now we know how to do that because that's called a half adder. The result of that needs to be added to another bit. So that's going to require another half adder. Okay, and we can draw a little schematic for a half adder. So it has an input, it produces some sum, and it produces some carry value. So what we want to do is we've got a carry in value that we also want to add to whatever this sum is. So we're going to put another half adder on, and we're going to add to that whatever the carry value is, and that will produce our final sum. That will produce a carry. Now we've got these two hanging carry values and we've got to somehow do something to these to produce what we call carry out. What I'm going to try and explain in this bit is how we determine what to do with the carry values. Okay, because the half adder bit is, to be fair, pretty obvious. We add the A and B together, get an answer, then we add the C to that answer to get the final answer. Okay, which is what that's showing us there. But it's not very clear as what we're doing with these carries. So I've drawn up all the combinations of two bits and carries to try and explain this. So let's give it a whirl. Okay, so our first set is to have A and B as 0 with a carry of 0. So let's just go through the basic maths of this. So we're going to say 0 and 0, and we can only add two bits at a time. So 0 and 0 is 0. Carry 0 for that bit. A carry was produced. That's critical. Okay. Then we get the carry and we want to add it to the result. So we're just following this schematic. So we're going to say 0 and 0 is 0. Carry 0. So we've generated these two carries. So I'm going to call that carry 1 and I'm going to call this carry 2. Okay, so that's the carry 1 is when we just add the two bits together. Carry 2 is produced when we add the result to the carry in. So I'm going to follow that format through. Okay, so we've got 0, 0. Right, so the other combination of A and B being 0 is when the carry is 1. So we get 0 and 0 is 0. Carry 0, that was C1. 1, which is the carry, and 0 is 1, carry 0. That's C2. Okay, so in this case, S was 0, S was 1. Or S out, let's call it S out. That's what it was. Okay, let's carry on. So I'm going to complete all these, and then we'll have a look to see if there's any relationship between the carries to see what we need to do with them. Okay, so we've got 0 and 1 for A, so that's 1, carry 0. The carry 0 and 1 is 1, carry 0. Right, let me just label these C in just to make that tie up as well. I'll do that as I go along. Okay, carrying on. So next combination is to have A is 0, B is 1, but the carry is 1. So we say 0 and 1 is 1, carry 0, so that's carry in. that's C1. And then we say 1 and 1 is 0 carry 1. So that was C2. So the sum out that time is 0. The sum out when we didn't have a carry was 1. Okay, let's move on. So the other combination is basically just the A and B flip. So A is 1, B is 0. So that's 1 carry 0. So that's C1, that's C in. Then we add the carry in to the result, or the intermediate result. So 0 and 1 is 1 carry 0. So C2 this time, and S out is 1, C2 is 0. Okay, move on. So with the carry set to 1 this time, so 1 and 0 is, it is not 0. 1 and 0 is 0. No, not. I've got ahead of myself doing the carry. 1 and 0 is 1 carry 0, so that's C1, that's C in. And then we add the carry to the intermediate result. So 1 and 1 is 0 carry 1. So C2 is carry 1. So the sum out is 0, but the carry has got a 1. Okay, which is what we'd expect because we've got 2. So that's 0 carry 1. Moving on. So when A and B are both 1, the carry is 0. What do we get? So we get 0 carry 1. So C1 is 1. So that was carry in. Then we add the carry in to the intermediate result. So 0 and 0 is 0 carry 0. Okay. And then the final one is where we've got a 1 and a 1 in A and B, and the carry in is 1. So let's add it up. So we get 1 and 1 is 0 carry 1. That was C1. And then we get the carry in added to the 0. So we say 1 and 0 is 1 carry 0. So that's C2. So that's what we'd expect. Okay, so when we add 3 together, we get 1 carry 1. When we add 2 together, we get 0 carry 1. When we add 2 together, which is what we're doing, we get 0 carry 1. When we add 1 together, we get 1 carry 0. When we add 2 together, we get 0 carry 1. Remember, the S out is the important one, not the intermediate one. When we add 1, 0 and 0 together, we get 1 carry 0. When we add 0, 0 and 1 together, we get 1 carry 0. When we add 0, 0, 0 together, we get 0 carry 0. Okay? So, in the circumstances where we've got 3, we expect to get a carry of 1. Where we've only got 2, we want the carry to be 0. Where we've got 3 numbers and 1 and 0, we expect the carry to be 1, because that's 2. Okay, just rub that off. I'll come back, I'll draw it again in a sec anyway. Where we've got 1, we expect the carry to be 0. Where we've got 2, we expect the carry to be 1, because it'll always be 0 carry 1. Where we've got 1, we expect the carry to be 0. Where we've got 1, we expect the carry to be 0. And obviously in the first case, we will expect the carry to be 0. Okay. So if we look just at C1, when it's 0, we get 0. 0. It's 0. Let's put C1 on there. C2. It's 0, but we get a 1 because of carry 2. 0, we get a 0. It's 0, but we get a 1 because of carry 2. It's 1, and that should be a carry of 1. Silly mistake. It's C1 is 1, so we get a carry of 1. C2 is 0. Now, in this case, we've got C1 is 1, and we've got a carry of 1. Okay, so we did 1 and 1, which is 0, carry 1, 1, 0, which was 0 and 1, which gave us 1 carry 0. So you can see that there are 4 cases where we get a carry. Okay, and that is where C1 is 0, C2 is 1. This one is where C1 is 0, C2 is 1. Okay. This one is where C1 is 1 and C2 is 0. This one is where C1 is 1 and C2 is 0. So the only time we get a carry, okay, is where we've got a 1. So you can see that, and just fill in these other ones, C1 and C2 are both 0. 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 Okay? So if you look at it like that, so they're both 0, get a 0, both 0, get a 0, both 0, get a 0, one of them's 1, we get a 1, both 0, get a 0, one of them's 1, we get a 1, one of them's 1, we get a 1, one of them's 1, we get a 1. And when we've got two values, and we get that as a result, so if we just call this carry out, so we're saying if they're both 0, we get 0, but if there's a 1, we get a 1. That is our good friend OR, okay, which has got the hardest symbol to draw, that logic symbol. So that's going to represent our carry out. So what we're saying is, if one of the carries is set, we want a 1. So that's the OR symbol. So we complete our full adder diagram, okay, and I'll just do it down here. So that's A and B and C in. So I'm doing it through the schematic, and I'll do a full diagram in a minute. I'll rub everything off. So we get A and B in. We get the, I'll call it S1, okay. That's going to get added to the carry in the other half adder. So we've got a half adder, we've got a half adder, and the resultant S out, is the final sum part. We're going to get two carries, but we've just determined that carry 1 and carry 2, if we OR them together, that will give us our actual carry out. Okay, and that's the full reasoning behind it. You don't have to necessarily remember all that. This diagram is actually quite easy to remember, okay, because it is just two half adders. So you add the A and B, the sum of that, add to the carry in, and then just remember that you OR the carries together. Okay, so that's it in schematic form. That's the proof of why the carry is ORed. Let's just look at it in full logic form. And what I'm going to do is I'm going to draw the half adder boxes, and I'm going to draw the circuitry inside. Okay, so I'll leave the little schematic there for reference as I'm doing this. Various ways of drawing this, and some you'll find some diagrams on the internet that move all the logic circuits around, but this is a better way of doing it, I think. So I'm going to draw one half adder, and I'm going to put two inputs. That one's going to be A, that one's going to be B. That's a half adder. I'll put it in the middle actually. I'll put it above it. That's going to have, so I'm going to have an output coming out of there, so I'm going to do it there like that. That is going to go into the next half adder and be combined with the carry in value, C in, and that's going to come out and generate S out, and then we're going to have a carry value which is going to come out of that one, so that's C1, that's C2, and we're going to combine those together with an OR, which is what we've just proved, give us the carry out. Okay, so I just need to do the wiring inside. So we know that the carry was produced by an AND gate. So let's draw an AND gate for each one of those carry outputs. So going into that are the two values. We need an Xor gate. So, oh dear, not very easy to draw. As long as it doesn't look like your AND gate, you should get away with it. But you must make sure you do that extra line for the carry. So I want B to go in there, but I also want B to go in here. So I do a spur. I want A to go in there, but I also want A to go into the AND gate, because they're both responsible for doing that. Do it again. So I'm going to make that input go in a bit lower. So that goes into there, but I also want it to go into my OR gate, Xor gate. I've done a little bit of a treat there. So I take my input into the Xor gate and I also send it into the AND gate. So that's the full schematic for a full adder. Okay. Now, this only adds 2 bits and a carry together. So we have a little diagram overview schematic for a full adder, and we tend to draw it like this, just a block which has 3 inputs, A, B and C in, but produces, we put full adder, S out and C out. Okay, so that will add 1 bit together. But what we would do if we wanted to actually do something useful, and we wanted, let's add 4-bit values together, or 8-bit values, or 16-bit values, we need to have a chain of full adders. So let's have a look at what that might look like. So I need to rub all this off. Okay. But rather than drawing lots and lots of logic symbols, we're going to use that little rectangular or square schematic. Okay, so I'm going to add 2 4-bit numbers together. So those numbers are going to be A3, A2, A1, A0, and that's not a very good B, and B3, B2, B1, and B0. So we're going to add those together. Okay, so that's a 4-bit value. Least significant bit is bit 0. Most significant bit is bit 3. Okay, so that's what we're going to attempt to do. So I'm going to draw, and there's a million different ways of doing it. I'm just doing it this way. So I'm going to draw a full adder. I'm going to draw 4 of them, because that's what I'm going to need, 1 for each bit. So I'm going to draw 4 boxes with FA in them. Like I say, there's a load of ways of doing this. So that's full adders. Now coming into this, we're going to have A and B. So we've got B0 and A0. I'm just going to put those on each one of those. So that's the bits for each number. So that's B1, A1. What way round doesn't really matter as long as you're consistent. Oops. That's A2 and B2. This one is A3 and B3. Okay, and we know that what we get is we get a sum for each thing. So that's going to be some 0, some 1, some 2, some 3. So let's put those on. So we're going to have some 0 come out, some 1, some 2, some 3. Now, so that's covered that symbol, and that symbol. There's another input and another output. So let's handle the inputs. So let's put our C in. Okay, and we've got a C out. So what we want to do is any carry from this operation, we want to feed into the input of this one, and then the input of this one, and then the input of this one, and then we'll have a carry out at the end. So the final carry out, which will go into the carry bit, okay, in the arithmetic and logic unit, in the condition code register, okay, that comes out at the end, pops out. So you can see we've got the 1, 2, 3, 4, so we just need the input. So we're going to just show carry out, carry in. Carry in, carry out. So we're just showing that the carry goes from one full adder to the next. Okay, so it comes out of this one, so it's going in that direction, and it pops out at the end. Okay, so that's a full adder for 4 bits. Obviously, and there's lots of different ways of doing this. This one like moves the carry along, so you have to do this bit once, then you can add these 2 bits, then you can add these 2 bits, then you can add these 2 bits. There are other ways of doing it to like predict the carry, but that's way beyond what we need to worry about. Okay, so this is a full adder for 4 bits. Each one of these is 5 gates. Each one of those. So to add 4 bits together, we could create a nice little circuit, and it'd be a great little exercise if you were doing electronics to make something like this. We would need 20 gates. Okay. If we want to add 2 10-bit numbers together, we'd need 40 gates. So a 10-bit adder would need 40 gates. Okay, and so on. So if you're doing 64-bit arithmetic, you're going to need 64 times 4, which is 256. So a 64-bit adder is going to need, no, that's a rubbish bit of arithmetic. It's 256 plus another 64, which gives us a horrible number. I'm really bad at mental arithmetic. If you ever watched any of my videos, let's add it up. 256 plus 64. That's no carry 1, which is topical. So that's 5, 11, 12, carry 1. Oh, 320. Yeah. So we need 320 gates to add 2 64-bit numbers together. But you wouldn't add 64-bit numbers using this structure of full adder. You would use some predictive carry system. Okay, so that's 2 really awesome circuits, and that feeds into work on CPUs. So this is really what CPUs have got inside them, these nice little circuits. It's nice that what you can see is a process that we do can actually be bolted down to some simple logic and then replicated. I find it quite nice. Okay, so that's the full adder.